March 16, 1980, Mount St. Helens had been quiet for more than a century. Rising above the forests of southwestern Washington, its snow-covered cone was considered dormant, monitored but largely ignored, a volcano that belonged more to geography textbooks than emergency planning. That perception changed abruptly when a series of small earthquakes began registering beneath the mountain. At first, the tremors were weak and scattered, barely perceptible at the surface. But to the seismographs operated by regional monitoring stations, the pattern was unmistakable. The earthquakes were shallow, clustered, and increasing in frequency. Something beneath Mount St. Helens was moving. On March 20, a magnitude 4.2 earthquake struck directly under the volcano. It was the strongest seismic event recorded in the area since modern monitoring began. Within hours, it was clear that the activity could not be dismissed as routine tectonic noise. The mountain was reawakening. Scientists from the United States Geological Survey were alerted, and within days, teams began mobilizing toward the volcano. Their mission was to determine whether Mount St. Helens was experiencing a temporary episode of unrest or the early stages of a renewed volcanic system. Portable seismometers were deployed around the mountain, often requiring long hikes through snow-covered terrain. The instruments confirmed magma beneath the volcano, fracturing rock as it ascended. The signals were persistent and organized, indicating pressure building within the volcanic conduit. On March 27th, Mount St. Helens produced its first eruption in over 100 years. Steam-driven explosions blasted ash and debris from the summit crater, sending dark plumes into the sky. These eruptions were relatively small, but they marked a critical transition. The volcano was no longer dormant, it was active. Over the following days, repeated steam explosions enlarged the summit crater, removing snow and exposing fresh rock. Each eruption reshaped the top of the mountain, carving deeper into its structure. As April began, scientists observed a new and alarming development. The north flank of Mount St. Helens began to deform. Instead of erupting vertically, magma accumulated beneath the volcano's northern side, forcing the surface outward. A massive bulge formed, visible even to the naked eye. Measurements revealed that the north face was moving outward at a rate that shocked researchers. In some areas, the deformation exceeded 1 meter per day. This was not a gradual swelling. It was rapid, sustained, and accelerating. Scientists documented the bulge through repeated surveys, laser measurements, and aerial photography. The deformation was unlike anything previously observed in the contiguous United States. It suggested that a large volume of magma was intruding laterally rather than rising directly toward the summit. The implications were uncertain. While flank deformation had been identified in ancient volcanic deposits elsewhere in the world, few modern eruptions had been observed closely enough to provide direct data. Mount St. Helens was becoming a live experiment under dangerous conditions. As activity continued, local authorities responded by establishing restricted zones around the volcano. Roads were closed, and residents living within designated danger areas were ordered to evacuate. The evacuations were contentious. Some residents complied immediately, while others resisted, convinced the mountain posed little threat. Law enforcement checkpoints were established to enforce closures, though exceptions were sometimes granted under supervision. Scientists were among those permitted access beyond the roadblocks, operating under special authorization. Observation posts were established on ridges and clearings north of the volcano, selected for their clear views of the growing bulge. From these locations, scientists could track changes in the mountain's shape and behavior in real time. Each day, teams returned to these posts, often before dawn, to collect measurements, photograph the bulge, and record seismic data. The work was systematic and methodical. The atmosphere among the researchers was focused, professional, and increasingly tense. By mid-April, Mount St. Helens had become one of the most closely monitored volcanoes in the world. Seismic stations recorded hundreds of earthquakes per day. Gas emissions fluctuated, indicating changes in pressure within the magma system. The bulge on the north flank continued to grow, pushing outward like a slowly inflating wall. Calculations showed that the overlying rock was being held in place by internal strength that could fail suddenly if disturbed. Despite this, the volcano did not erupt explosively. Instead, it remained in a state of unstable equilibrium, active but contained. This prolonged unrest created a complex challenge for scientists and authorities alike. The mountain was clearly dangerous, but without a clear trigger or timeline, decisions about access and safety were difficult. As April turned into May, the deformation showed no signs of slowing. The north flank bulge grew larger and steeper, its surface fractured by tension cracks. Aerial surveys revealed that the mountain's profile was changing day by day. Scientists debated possible scenarios. Some believed the pressure would eventually be released through a vertical eruption. Others warned that the bulge could collapse catastrophically, releasing energy sideways rather than upward. The latter scenario was based on geological evidence from past eruptions at other volcanoes, but it had rarely been observed directly. Mount St. Helens was presenting conditions that challenged existing models. On May 7th, officials expanded the restricted zones, closing additional areas north of the volcano. Despite these measures, several observation posts remained within what would later be recognized as the potential blast zone. At the time, those boundaries were based primarily on expectations of vertical fallout, not lateral destruction. Scientists continued working from these locations, aware of the danger, but constrained by the need to remain close enough to collect meaningful data. Their presence near the volcano was not casual. It was the result of calculated risk, shaped by incomplete knowledge and the urgency of the situation. By May 15th, seismic activity intensified again. Earthquake frequency increased beneath the volcano, though magnitudes remained moderate. Gas emissions changed, suggesting shifts in pressure within the magma body. The bulge on the north flank reached its maximum recorded size, jutting outward dramatically. Photographs taken during this period show the mountain visibly distorted, its once symmetrical cone now misshapen and unstable. Scientists documented these changes meticulously, aware that the data they were collecting was unprecedented. On May 17, Mount St. Helens remained active, but deceptively quiet. There were no major explosions, no dramatic ash columns rising into the sky. To the casual observer, the mountain appeared restless but contained. To those monitoring it closely, the signals were troubling. The internal pressure was high, and the structure of the north flank appeared critically weakened. That evening, scientists finalized plans for the following day's observations. Teams prepared to return to established posts to continue measurements at first light. The routine had become familiar after weeks of monitoring. Instruments were checked, cameras readied, and observation schedules confirmed. There was no specific warning that May 18 would be different from the days before it. Before dawn on May 18, 1980, cloud cover hung low over Mount St. Helens. Snow still blanketed much of the upper slopes, and temperatures remained cold at higher elevations. At 7 a.m., seismic instruments recorded small earthquakes beneath the volcano, consistent with ongoing activity. The data did not indicate an imminent eruption. The mountain looked much as it had the previous day, its north flank bulge looming silently above the forests below. Scientists took their positions, unaware that the conditions they had been documenting for weeks were about to reach a critical threshold. At 8:32 a.m., a magnitude 5.1 earthquake struck directly beneath Mount St. Helens. The tremor was strong enough to be felt miles away. Within seconds, the already weakened north flank began to fail. The bulge collapsed catastrophically, initiating the largest landslide ever recorded. A massive section of the mountain slid away, removing the weight that had been containing the pressurized magma and gas beneath. The sudden decompression triggered a lateral blast, an explosion directed sideways through the collapsing flank. the blast accelerated outward at supersonic speed, carrying superheated gas, ash, and rock across the landscape north of the volcano. Temperatures within the blast exceeded hundreds of degrees. Forests were flattened instantly. Snow, soil, and debris were stripped from the ground. The destruction was total and immediate. Observation posts north of the volcano were engulfed within seconds. Instruments stopped transmitting mid-recording. There was no opportunity for communication or escape. Simultaneously, an enormous vertical eruption column rose from the newly formed crater, punching tens of thousands of feet into the atmosphere. Ash began falling across Washington, turning daylight into darkness in communities far from the volcano. Rivers filled with debris, roads were buried, and air traffic was halted as ash clouds spread eastward. The eruption continued for hours, reshaping the mountain and altering the surrounding landscape beyond recognition. As emergency systems activated, officials struggled to assess the scale of the disaster. Communication with areas near the volcano was impossible. The blast zone remained inaccessible due to ongoing hazards, unstable terrain, and continued volcanic activity. By midday, it was clear that Mount St. Helens had experienced one of the most violent eruptions in modern history. What was not yet clear was who had been caught in its path. Initial reports were fragmented. Scientists, law enforcement officers, and civilians who had been near the volcano were listed as missing. Rescue efforts were delayed as authorities waited for conditions to stabilize. The mountain continued emitting ash and steam, and debris flows surged through river valleys. As ash clouds drifted across the continent, the immediate aftermath of the eruption unfolded in confusion and uncertainty. By the end of May 18, aerial surveys began revealing the extent of the devastation. Entire forests lay flattened in a radial pattern extending miles from the volcano. The north face of Mount St. Helens was gone, replaced by a vast crater open to the sky. Within the devastated zone were the locations where scientists had been conducting observations. There were no visible signs of human presence. Vehicles, equipment, and structures had been obliterated. The mountain had erased them completely. As night fell, the focus shifted from monitoring the eruption to accounting for those who had been working near the volcano. The list of missing scientists grew, and the realization set in that some had been too close to survive. Understanding how they came to be there, what they knew in the final days before the eruption, and how decisions were made as the danger escalated would require careful reconstruction. That reconstruction would begin not with the explosion itself, but with the choices made during the weeks of unrest that led scientists to remain near Mount St. Helens as it approached the moment of catastrophic failure. In the hours immediately following the eruption, Mount St. Helens remained unreachable. Ash continued to fall across the region, visibility dropped to near zero, and debris flows surged through river valleys fed by melted snow and volcanic material. Roads leading toward the mountain were buried or destroyed, and helicopters were unable to approach due to unstable air conditions and drifting ash clouds. Emergency coordination centers received only fragmented information from locations farther away, while all communication from the blast zone had ceased. The volcano continued releasing steam and ash intermittently, raising concerns that additional eruptions could follow. As long as seismic activity persisted beneath the crater, no recovery or investigative efforts could begin. The first priority was determining whether the eruption was over or if further collapses were likely. Only after several hours, when eruptive intensity decreased, were limited reconnaissance flights approved to survey the damage from a safe distance. From the air, the destruction was immediately apparent. North of the volcano, an immense area had been flattened, its forests stripped and laid down in a uniform direction away from the mountain. The terrain appeared scoured to bare ground, with soil, vegetation, and snow removed almost entirely. Within this zone were the known locations of scientific observation posts that had been occupied during the preceding weeks. No structures were visible. Vehicles, shelters, and instruments had either been destroyed or buried beneath ash and debris. As aerial surveys continued, authorities began compiling a list of individuals who had been authorized to operate inside restricted areas on the morning of May 18th. Permit records, vehicle checkpoints, and radio logs were reviewed to determine who had been present near the volcano at the time of the eruption. The list included several scientists who had been conducting routine monitoring from fixed observation points north of Mount St. Helens. These positions had been selected for their clear view of the north flank bulge and had been used repeatedly in the days leading up to the eruption. On the morning of May 18th, at least one scientist had reached his post early, preparing to continue measurements under conditions that appeared unchanged from previous days. His final radio transmission reported no unusual activity beyond the ongoing seismic unrest. Shortly afterward, all contact was lost. Other scientific teams had been operating from mobile positions farther from the volcano. Some of these teams survived and later described the moment the eruption occurred. They reported a sudden shock wave that knocked them to the ground, followed by a rapid loss of visibility as ash and debris filled the air. Several described feeling a brief surge of heat before retreating to safer ground. These accounts helped establish the outer limits of the lateral blast and confirmed its extraordinary speed and force. In contrast, those stationed closer to the volcano left no first-hand testimony. Investigators relied on indirect evidence to reconstruct their final positions. The locations of destroyed instruments, collapsed measurement stakes, and displaced equipment provided clues about where individuals had been standing at the moment the blast arrived. Seismic data from stations located farther away recorded the precise timing of the triggering earthquake and the subsequent collapse of the north flank. By comparing this data with known distances, analysts determined that the lateral blast reached nearby ridges within seconds. The speed of the blast meant there was no opportunity for escape or communication. In the days that followed, access to the outer edges of the blast zone was gradually permitted under strict controls. Teams moved cautiously across unstable terrain, aware that ash deposits could collapse without warning and hot material might still be buried beneath the surface. Their task was documentation rather than recovery. Every identifiable landmark, displaced instrument, and fragment of equipment was photographed, mapped, and recorded. In some cases, twisted metal from scientific instruments was found embedded in the ground, indicating the tremendous mechanical force of the blast. Personal effects were rare. The combination of heat, pressure, and debris had left little intact. In several areas, nothing remained to indicate that people had been present moments before the eruption. As documentation progressed, investigators examined the sequence of decisions that had placed scientists within the blast zone. During the weeks of unrest, access to Mount St. Helens had been controlled through a permit system that allowed scientists to cross roadblocks and enter restricted areas to conduct monitoring. These permits were issued with the understanding that access could be revoked if conditions worsened. However, the prolonged period of activity without a catastrophic eruption had created a routine. Observation posts were visited daily, and despite the growing deformation of the north flank, continued access was considered acceptable under existing guidelines. Field notes and internal communications from the period show that scientists were aware of the instability of the bulge and the possibility of a collapse. However, estimates of the potential scale varied widely. Some scenarios envisioned a limited failure of the upper portion of the flank, while others allowed for a larger collapse but did not fully account for the energy that would be released by rapid decompression of magma.
At the time, hazard planning focused primarily on vertical eruption threats, such as ashfall and ballistic debris. The potential for a massive lateral blast had not been fully incorporated into operational boundaries. The triggering earthquake that struck at 8:32 a.m. on May 18th was moderate in magnitude, but it occurred beneath a structure that had been weakened by weeks of deformation. The collapse of the north flank was immediate and complete, removing the weight that had been containing the magma and gas beneath. The resulting lateral blast traveled outward at extreme speed, devastating everything in its path. Over the following days, the list of confirmed fatalities among scientists was finalized. Their deaths were attributed to the lateral blast and its associated thermal and mechanical forces. In several cases, the lack of recoverable remains meant that precise causes could not be determined. What could be established was that their positions placed them directly within the zone of maximum destruction.
As Mount St. Helens settled into a new phase of activity, attention turned towards long-term monitoring and documentation of the altered landscape. The crater left by the collapse became the focus of ongoing study, with scientists tracking changes within the exposed interior of the volcano. Each new observation was made from a distance under revised access controls shaped by the events of May 18. The story of the scientists who stayed near Mount St. Helens extended beyond the eruption itself. It encompassed the final days of monitoring, the positions they occupied, and the rapid sequence of events that left no opportunity for escape. Their absence became part of the landscape surrounding the volcano, reflected in empty observation sites and destroyed equipment. This account concludes with the immediate aftermath as the mountain transitioned from violent eruption to a period of continued activity and recovery operations began. Thank you for watching and following this story to the end. If you enjoyed this video and want to see more real histories like this one, consider subscribing to the channel and leaving a comment with your thoughts. Your support helps keep these stories alive.